Hello there, and welcome to the Last Signal channel. Tonight, we are leaving behind everything the solar system taught us to expect from a planet. Beyond our own star, familiar words begin to fail. Day may no longer arrive. Ground may never exist. An ocean may hide beneath crushing layers, while a sky can slowly disappear into space. Some worlds are shaped by forces so intense that they seem less like places and more like unfinished physical events. Others move in arrangements that would look impossible if our own planetary system were the only example we had. For centuries, humanity built its idea of a planet from a tiny local sample. Then distant stars began revealing worlds that refused to fit inside it. What astronomers found did more than expand a catalog. It changed the boundaries of the word itself. These planets show how gravity, heat, chemistry, radiation, and chance can combine in ways no single definition can fully contain. And the more clearly we learn to detect them, the less certain our old categories become. If you enjoy calm documentaries about space, science, and the unanswered questions beyond our world, subscribe to The Last Signal on YouTube. Because somewhere in the darkness, another planet is already forcing us to rethink what a world can be. From across interstellar space, most stars appear completely alone. No neighboring body can usually be separated from their glare, and no surface, cloud, or orbit is visible beside them. Yet a hidden world does not need to produce its own picture to reveal that it exists. It only needs to disturb something astronomers can measure. One of the clearest disturbances is a small, repeating drop in starlight. When a planet passes between its star and Earth, it blocks a tiny fraction of the light reaching our telescopes. This event is called a transit, and its pattern can reveal much more than a passing shadow. The depth of the dip provides an estimate of the body's size relative to its star. The time between each dip shows how long one complete orbit takes. If the signal returns regularly, it resembles a tiny mark repeatedly crossing the face of a faraway lamp. The world remains invisible, but its shadow keeps time. This method works only when the orbit is aligned correctly from our point of view. Most systems are tilted in other directions, so their companions never cross the stellar disk as seen from Earth. For those systems, astronomers can search for motion instead. A star with an orbiting companion does not remain perfectly still. Both objects move around a shared center of gravity, although the star's movement may be extremely small. As it shifts slightly toward Earth and then away again, its light changes in a measurable pattern called radial velocity. The repeated motion can reveal a hidden companion and provide information about its mass. A massive body usually produces a stronger stellar wobble, while a smaller one leaves a weaker effect that can blend into the star's own activity. Transits reveal size, while radial velocity reveals how strongly the hidden object pulls. Together, the measurements allow astronomers to estimate average density and begin separating rocky bodies from gas-rich giants. Another method begins with the light of a much more remote background star. When a foreground star passes across that line of sight, its gravity bends and magnifies the background light for a short time. An orbiting planet can add a smaller disturbance to that temporary brightening. The effect is called gravitational microlensing. Unlike a repeating transit, the alignment may happen only once before the stars continue moving apart. Microlensing can therefore reveal remote systems and wide orbits that other surveys often miss. It is a temporary window opened by gravity and closed by motion. Some worlds beyond the solar system can be photographed more directly, although the challenge is severe. A star is so much brighter than its companion that separating them is like identifying a firefly beside a floodlight from an enormous distance. Newly formed massive giants provide the clearest targets because they still retain heat from formation and glow strongly in infrared light. In a successful direct image, the object may appear only as a faint point beside the reduced glare of its star. The image does not reveal continents, storms, or oceans. Yet that weak point is not a diagram or a prediction. It is light that traveled from the object itself. A dim, heated trace hangs beside its star, surrounded by darkness and divided from Earth by years of empty space. The achievement lies in how little light had to be isolated before another world emerged from the glare. Even when no companion can be photographed, the material around a forming star may reveal where one is developing. Disks of gas and dust can contain gaps, rings, spirals, warps, or regions where matter moves unexpectedly. An unobserved body may clear a path through the disk or pull nearby material into a distorted pattern. These structures do not prove that a planet is present in every case, because disk physics can produce some features without one. They remain indirect evidence, strongest when several measurements support the same explanation. Each method also favors certain kinds of objects. Transits favor bodies whose orbits cross their stars from our perspective, while radial velocity works best when a companion creates a strong repeating motion. Direct imaging favors newly formed, infrared bright giants far from stellar glare, while microlensing reaches remote systems through brief events that may never repeat. These preferences shape the catalog astronomers build. The first discoveries were often not the galaxy's most common worlds, but simply the easiest ones to detect. Size, orbit, temperature, distance, and alignment decide which signals rise above an instrument's limits. The known population is therefore filtered by geometry, sensitivity, timing, and the methods available to us. A shadow can reveal size, but it does not directly show a surface. A wobble can reveal mass, but it does not describe an atmosphere. A spectrum can identify certain gases, but it cannot provide a complete climate. A gap in a disk can suggest a concealed object, but it does not preserve the system's entire history. Observation must come first, and interpretation must remain tied to what the instruments actually recorded. Bodies too faint to see can still be weighed, timed, compared, and tested. Astronomers reconstruct them from a shadow, a wobble, a distortion, or a warm point beside a star. Before these planets become places in the human mind, they exist as effects. And from those effects, entire worlds slowly take shape. On some planets, an entire year ends before an ordinary afternoon on Earth is over. These bodies circle so close to their stars that one complete orbit may take only a few hours. The familiar calendar loses its meaning under those conditions. A year is no longer a long measure of seasons, growth, and changing weather. It becomes a rapid loop repeated again and again beneath an overpowering star. An orbital period simply measures how long one body takes to circle another. The smaller the path around the star, the less distance must be covered before the circuit begins again. Gravity also pulls more strongly at close range, forcing the moving body to travel at tremendous speed. It resembles a runner circling a very small track, completing repeated laps, while someone on a larger track is still approaching the first turn. For an ultra-short period planet, months and seasons may have no useful equivalent at all. Its calendar may advance faster than its surface can rotate. That creates one of the strangest possible reversals in planetary time. A day can last longer than a year. The body may complete several circuits around its star before turning once fully around its own axis. From the surface, if any solid ground existed, the movement of the star across the sky could be painfully slow. Meanwhile, the orbital calendar would continue advancing at extraordinary speed. Time itself has not changed. The units only describe different forms of motion, and those motions do not need to remain in familiar proportions. Close proximity also changes far more than the calendar. The star dominates almost every physical condition on the nearby body. Radiation pours into the upper atmosphere, heating gases and breaking apart molecules that would remain stable farther away. The star's gravity pulls unevenly across the near and far sides, creating strong tidal stress. That constant distortion can heat the interior, alter the atmosphere, and gradually change rotation. Over long periods, gravitational friction drains energy from the original spin. The rotation slows until the same side continually faces inward. This condition is known as tidal locking. It does not mean the planet has stopped moving. The body continues racing around its star while turning at exactly the rate required to keep one face directed toward it. The effect is similar to the moon always showing nearly the same side to Earth. On a close exoplanet, however, the star may appear far larger and more intense than the sun appears from here. It could hang in almost the same place overhead, filling the sky with light that never crosses towards sunset. Beneath it, repeated years would pass without a single sunrise or evening. The orbital motion would be fast, yet the sky could appear almost frozen. Astronomers did not expect every giant planet in these close positions to have formed there. The inner region around a young star is extremely hot and often contains too little suitable material to build a gas giant easily. Many hot Jupiters probably began farther out, where colder conditions allowed large cores and thick envelopes to assemble. Later, those giants moved inward. Orbital migration is the leading explanation for many of these systems, although individual histories may differ. During the early life of a planetary system, gas, dust, and multiple growing bodies all exert gravitational influence. A giant moving through that crowded environment can exchange energy with the surrounding disk. It may also interact with neighboring bodies and shift into a tighter path. The movement can continue until the surrounding gas disappears. Another object interrupts the process, or the planet reaches a stable configuration. This inward motion is not gentle for everything nearby. A heavy giant passing through a young system can disturb smaller bodies, alter their paths, and trap some of them in repeating gravitational relationships. Others may collide, fall toward the star, or be thrown into distant regions. The final arrangement can therefore hide a far more unsettled beginning. A close giant may look stable today because the most disruptive phase ended long ago. Its current position preserves only the result. The missing bodies, altered paths, and redistributed material are much harder to recover. In some systems, migration may occur smoothly through interaction with the original disk. In others, several giants may pull against one another until one is driven inward and another is pushed outward. Calculations allow multiple routes to the same final configuration. That is why astronomers treat the present orbit as evidence rather than a complete explanation. A tight path reveals the conditions that exist now. It does not automatically identify every force that placed the body there. The difference matters because the orbit influences almost everything that follows. Temperature, atmospheric loss, tidal heating, rotation, and long-term survival all depend on distance from the star. A slight change early in the system's development can produce a completely different planet later. One body may remain cool enough to preserve a thick atmosphere. Another may move inward until its upper gases begin escaping into space. A third may experience enough tidal stress to keep its interior active for ages. The same initial ingredients can therefore produce sharply different outcomes. Viewed from far away, an ultra-short orbit may seem simple. The planet follows the same narrow path, circuit after circuit, with mechanical regularity. Yet that repeated motion carries the record of radiation, friction, migration, and lost neighbors. Every short year is the visible result of a much longer history. The present orbit may be only the final address of a world that formed somewhere else. WASP 76b is a giant planet where its gaseous envelope becomes hot enough for iron to exist as vapor. On the side facing its star, temperatures rise so high that material familiar as solid metal can enter the upper gases. There, iron is not part of a mountain, a tool, or a buried layer of rock. It becomes part of a moving climate system. Strong circulation can carry that vapor away from the hottest region toward cooler parts of the atmosphere. As the gas loses heat, some of the iron may condense into droplets before falling deeper into the cloud layers. This is why the world is often described as a place where metallic rain could fall. The phrase is vivid, but it is also a simplification. No camera has recorded metallic drops moving through a distant atmosphere. The interpretation comes from patterns in the surrounding gases, circulation models, and the way elements appear along different parts of the planet's edge. Evidence is consistent with the metal remaining gaseous under intense heating and condensing where conditions become cooler. That alone overturns an ordinary assumption about what skies can contain. On Earth, the lower atmosphere carries water, dust, salt, and gases, released by biological and geological processes. On ultra-hot giant planets, the same physical rules act on materials. Our environment usually keeps locked inside stone. Sodium, magnesium, and silicon-bearing gases can rise into the upper atmosphere, while severe heat can break molecules into individual atoms. The sky becomes a moving mixture of matter that would form cliffs, sand, or metal under gentler conditions. Rock can become weather. This transformation happens because condensation depends on temperature and pressure rather than on one special material. A cloud forms when part of the gaseous layer cools enough for a substance to leave the gas phase and collect into suspended particles or droplets. Here, that substance may consist of silicate grains, metal compounds, or other mineral substances. A cloud deck could therefore contain particles made from the ingredients of stone. From far away, the layer might appear smooth and continuous. Up close, it would be an environment of fierce heat, rapid motion, and matter repeatedly changing state. Mineral clouds could cross a dark hemisphere while hotter gases rise, and cooler matter sinks through the surrounding envelope. Far below, deeper layers would glow with heat that never reaches a calm, solid surface. The contrast between the star-facing side and the darker side can drive winds moving several kilometers per second. In some regions, that motion may exceed the local speed of sound. The result is not a simple stream from hot to cold. Rotation and pressure differences can produce broad jets, rising columns, and returning flows that carry energy around the globe. The entire envelope behaves as one connected system, with conditions in each region influencing places far beyond it. Yet these gases are never composed of fixed parts. Molecules break apart, atoms cross the planet, and new compounds form where temperatures allow them to survive. These changes can make the morning side and evening side chemically different. One edge rotates into daylight, while the opposite edge moves into darkness. At the hotter boundary, substances may evaporate or separate into atoms. At the cooler boundary, the same atoms may recombine or condense. Two sides of the same gaseous shell can therefore leave different signatures in starlight. Astronomers study those signatures through spectroscopy. When the planet passes in front of its star, a small fraction of the stellar light filters through the outer gases. Atoms and molecules absorb particular wavelengths, leaving narrow gaps in the colors that reach a telescope. The pattern can be separated much like a chord being divided into individual notes. Each missing portion points toward material capable of absorbing that wavelength. Researchers compare the observed pattern with laboratory measurements and physical models. This does not produce a complete photograph of the gaseous shell. It provides evidence about ingredients, temperature, motion, and sometimes differences between one side and the other. A thin ring of gas around a distant body can alter enough light to reveal vaporized iron, sodium, water vapor, or other substances. From that faint change, astronomers reconstruct a climate no spacecraft has visited. Hot rocky planets can push the same principle even further. If a surface becomes hot enough to melt and evaporate, the gaseous layer may be supplied directly by the crust below. Rocky material rises as vapor, moves with global circulation, and can later condense as the temperature falls. The boundary between geology and weather then becomes difficult to define. The ground feeds the sky, and the sky returns matter to the surface. It is less like a gaseous layer resting above a surface, and more like the planet slowly exhaling its own outer layer. Under those conditions, clouds, winds, and precipitation are not separate from geology. They are geology in motion. The remarkable part is not that these planets ignore familiar physics. Familiar physics simply produces unfamiliar outcomes when pressure, temperature, and composition change. Iron can rise as vapor, stone can form clouds, and minerals can cross a sky before returning to deeper layers. Weather is not a fixed collection of earthly events. It is matter responding to heat, pressure, and motion. 55 Cancri E is a rocky planet so hot that parts of its exterior may exist as an ocean of liquid stone. Seen from close above the surface, the horizon would not be defined by dark soil or pale dust. It would glow. The ground itself would release enough heat to shine through any thin gases above it. This planet circles extremely close to its star, receiving far more radiation than any rocky body in the solar system. Its measured temperature leaves little room for an ordinary solid exterior on the hottest side. Researchers still debate the exact distribution of heat and the detailed nature of its atmosphere. Even so, the available evidence points toward geology operating under conditions far beyond anything stable on Earth. A magma ocean is not simply a large pool of lava resting in one place. It can circulate, absorb stellar energy, transport heat, and exchange material with the gases overhead. Hotter liquid rises, cooler material sinks, and the entire outer layer may remain in slow, continuous motion. Pressure changes within the molten mass can also release gases that were previously trapped inside the rock. Those gases rise into the atmosphere and alter its composition. At the same time, material from above can dissolve back into the liquid below. The atmosphere and the surface, therefore, behave less like separate layers and more like connected parts of one system. Heat moves through both. Matter moves through both. The boundary between them may shift as temperatures rise and fall. 55 Cancri E may also retain a gaseous envelope despite the intense radiation from its star. That possibility matters because even a thin atmosphere can redistribute heat and change the difference between the bright side and the dark side. It can also hide parts of the surface from direct observation. Measurements reveal temperature and chemical traces, but they do not provide a complete map of lava flows, continents, or solid regions. Many of those details remain model-based interpretations. A second world, K2141b, offers an even more unusual possibility. Models of this close-orbiting rocky planet allow for a cycle in which surface material evaporates, enters the atmosphere, moves toward cooler regions, and later condenses. On Earth, water evaporates from seas, forms clouds, and returns as rain. On this hotter body, the working material may come from the crust itself. Sodium-bearing gases and other rocky components could rise above the molten side and travel with the atmospheric flow. Farther from the strongest heating, some of that material may cool and fall back toward the surface. The process resembles a planetary rock cycle compressed into the atmosphere. The ground does not merely erode beneath the weather, it supplies the weather. Over time, this circulation could move material from one region to another and gradually reshape the outer layer. No spacecraft has watched this cycle directly. It remains a physical model built from temperature, gravity, composition, and the behavior of rock under extreme heat. The model is valuable because it shows how familiar processes can reappear with entirely different materials. Evaporation does not belong only to water. Cloud formation does not require an Earth-like sky. Precipitation does not need to be gentle. Internal heat can keep such a world active even when stellar radiation dominates the exterior. A young rocky body may still retain energy from its formation. Radioactive elements can continue releasing heat within the mantle. Strong tidal forces may flex the interior as the planet moves through an uneven gravitational field. Each source contributes differently depending on the body's age, structure, and orbit. Tidal heating can be especially important when the path is slightly stretched or when neighboring objects disturb the motion. The repeated flexing acts like slow mechanical work inside the planet. Rock deforms, friction produces heat, and partially molten regions may persist far longer than size alone would suggest. A small planet is not necessarily a cold one. If the star supplies enough energy, the exterior can remain liquid even after much of the original formation heat has faded. If tidal stress remains strong, the interior can continue feeding volcanic activity from below. Persistent volcanism then becomes more than an occasional eruption. It can renew the entire visible exterior. New flows cover older rock, bury impact scars, and release fresh gases into the atmosphere. A surface shaped this way may never preserve a long, quiet record. The outer layer becomes like a page repeatedly erased and written over by new lava. Every impact mark, fracture, or ancient plane can disappear beneath younger material. The planet may look geologically young even after it has existed for an immense span of time. On the dark side, the appearance could be very different from the star-facing region. The sky might remain black while exposed fractures glow from below. Lava channels could trace slow lines across the darkness. Recently cooled plains might form a thin crust, only to split as heat pushes upward again. No sunlight would be needed to illuminate the terrain. The planet's own interior would provide the light. Across such a hemisphere, silence would not mean inactivity. Beneath the solidifying skin, molten material could continue moving, rising, and forcing new openings through the ground. The bright side might resemble a vast foundry, while the darker regions could carry scattered red fractures like heat escaping through broken stone. Yet even that comparison has limits. A foundry is controlled, contained, and temporary. This process could encompass an entire planet. The most important lesson is not that these worlds are simply hotter versions of Earth. Their surfaces, atmospheres, and interiors may operate as one connected cycle. Rock melts, gases escape, material circulates, and fresh crust forms before being destroyed again. Stability becomes temporary. Ground becomes a changing state rather than a permanent foundation. Some rocky planets are not settled places with occasional geological activity. They are continuous physical processes wearing the shape of worlds. On a tidally locked planet, the star does not rise, cross the sky, and disappear below the horizon. From one location, it remains fixed above the same point for as long as the orbit stays stable. The planet continues circling its star, yet its rotation matches that orbit so precisely that one side always faces the light. The opposite side never turns toward it. Day and night stop behaving like passing periods. They become places. A traveler moving across the surface would not wait for evening to arrive. They would walk toward it. The star-facing region receives constant energy, while the far side remains under continuous darkness. Between them lies the terminator region, the permanent boundary separating day from night. This border is not a thin line drawn across a map. It can form a broad band where the star hangs low near the horizon, and the incoming light strikes the surface at a shallow angle. Some climate models produce more moderate temperatures there than on either extreme side. That possibility has made the region a common focus in discussions of habitability. Yet permanent twilight does not guarantee comfortable conditions. Temperature depends on atmospheric pressure, composition, cloud cover, winds, oceans, and the strength of radiation arriving from the star. A thick atmosphere may carry large amounts of heat into the dark side. A thin one may leave the bright side scorching, while the far side grows cold enough for gases to freeze onto the ground. If an ocean exists, currents may transport energy beneath the atmosphere and soften the contrast between the two regions. Without enough circulation, the climate could divide sharply between heated and frozen environments. The planet is therefore less like two separate halves and more like one connected system struggling to redistribute an uneven supply of energy. Air warmed beneath the fixed star can rise and move toward cooler areas. At higher altitudes, it may cross into darkness before sinking and returning closer to the surface. Planetary rotation can bend these flows into broad jets, while pressure differences drive storms around the globe. The dark side is not necessarily motionless, and the bright side is not necessarily uniform. Clouds may gather over the hottest region and reflect part of the incoming radiation. In other areas, clear skies may expose the ground to stronger heating. The final climate emerges from the interaction of all these processes rather than from distance alone. Standing near the boundary, the star would remain close to the horizon. It would never climb into a full noon and never disappear into complete night. One direction might glow under permanent low-angle light, while the other faded into a colder sky. Shadows could stretch across the terrain without noticeably changing position. Hours would pass, but the sky would not advance with them. The border between brightness and darkness would feel less like a moment in time and more like a country that could be entered or left. Many planets likely to become tidally locked orbit red dwarfs. These stars are smaller and cooler than the Sun, and they are the most common type of star in the galaxy. Because they produce less light, a planet must orbit relatively close to receive enough energy for moderate surface temperatures. That close distance increases the strength of tidal interaction and makes locked rotation more likely. The same arrangement that places a planet within a potentially temperate region can therefore create permanent day and permanent night. Red dwarfs introduce another complication. Many release powerful flares and streams of charged particles, especially when they are young. A nearby planet may experience sudden bursts of high-energy radiation far stronger than those reaching Earth. These events can heat the upper atmosphere, break apart molecules, and help drive gases into space. Over long periods, repeated activity may thin an atmosphere or alter its chemistry. That outcome is not inevitable. A massive atmosphere may endure substantial loss and still remain dense. Volcanic activity may replenish gases from the interior. Magnetic effects can influence how charged particles interact with the planet, although they do not act as a perfect shield. The survival of the atmosphere depends on several competing processes operating over enormous spans of time. A red dwarf's color also does not mean the sky below would look like a simple red filter. The appearance depends on the wavelengths produced by the star and on how the surrounding gases scatter and absorb them. A clear atmosphere could create one visual effect, while haze, clouds, or airborne particles created another. The daylight might appear dimmer than Earth daylight while still containing a complex range of colors. Nearest the horizon, the fixed star could seem warmer in tone without turning the entire sky crimson. Any description remains conditional because the visual experience depends on an atmosphere that may be difficult to measure. The position of the light also changes how weather organizes itself. On Earth, continents and oceans rotate through sunlight and darkness, repeatedly gaining and losing heat. On a locked planet, the strongest heating remains centered over one region. Storms may gather around that constant source, while winds carry energy outward toward cooler zones. Cloud cover could form a bright reflective cap over the star-facing side. Elsewhere, atmospheric gases might condense as they cross into colder conditions. The circulation becomes a planetary transport system built around a fixed imbalance. This makes the terminator region especially complex. It may receive less direct radiation than the center of the bright side, while still benefiting from heat carried by air or water. It could also experience relentless winds produced by the pressure difference between the two larger regions. A moderate average temperature would not reveal whether the local environment was calm, violent, dry, wet, stable, or chemically hostile. Habitability cannot be reduced to standing at the correct distance from the light. The planet's entire system must cooperate. Tidal locking transforms familiar directions into physical conditions. Toward the star means greater exposure. Away from it means deeper darkness. Sideways can mean entering a narrow region where both influences meet. Latitude may still matter, but exposure to light can become the stronger organizing feature. A map of such a planet would not be divided only by mountains, oceans, or climate zones. It would also be divided by illumination. On these worlds, light is not merely something that falls across geography. Light creates the geography. A blue planet can look familiar from a distance. Clouds may drift across its face, and a smooth, reflective surface may suggest oceans like those on Earth. Yet color alone reveals very little about what lies beneath. A world covered almost entirely by liquid could contain no continents, no beaches, and no shallow coastal regions at all. The sea might extend around the globe without a single interruption. At first, that sounds like an enlarged version of Earth. In reality, the structure could become less familiar with every mile downward. Our deepest trenches occupy only a thin outer layer, compared with the possible seas on more water-rich planets. On such a body, the descent could continue long after sunlight had disappeared. Pressure would rise steadily as the weight of the liquid above increased. Eventually, the lower layers would stop behaving like any ordinary earthly ocean. The molecules would be forced into dense arrangements created by compression. This can produce high-pressure ice, a solid form of water that exists because of enormous pressure rather than cold surface conditions. The name can be misleading. It is not a frozen crust floating beneath a warm sea in the familiar sense. It is a compact layer formed where the pressure becomes strong enough to change the material's physical structure. A water-rich planet could therefore resemble a set of nested shells. Clouds and atmosphere would surround the outer liquid layer. Below that sea, dense compressed ice could form another shell. Farther inward, a rocky interior might remain completely separated from the open water above. That separation could matter greatly for chemistry. On Earth, seawater interacts with the crust through volcanic regions, fractures, erosion, and hydrothermal activity. Those contacts move minerals and chemical ingredients between rock and liquid. They also help maintain long-term cycles that influence the atmosphere and climate. If a thick layer of compressed ice sits between the sea and the rocky interior, that exchange may become far more limited. The planet could possess an enormous amount of water, while lacking the same access to minerals and energy sources found in Earth's oceans. An ocean can be vast and still be isolated from stone. The visible surface would reveal none of this. From space, the planet might appear serene, uniform, and almost inviting. Beneath the bright upper layer, however, the water would darken. Blue light would weaken first, followed by the remaining glow from above. The pressure would continue rising in complete darkness. No seafloor would appear at a familiar depth. The descent would pass through colder and warmer layers, changing density, currents, and chemistry along the way. Eventually, liquid would meet a solid barrier made from the same substance, under a different physical state. Below that compressed shell, the true rocky body could remain unreachable from the sea above. The calm blue sphere would conceal an internal structure, unlike anything visible from its clouds. Not every water-rich world needs an open global sea. Some may present the opposite appearance. A frozen exterior can cover a liquid reservoir kept warm beneath the surface. If enough energy remains inside the planet, the ice above can act as insulation and slow the loss of heat. Radioactive elements within the rocky interior may continue releasing energy over long periods. Tidal forces can provide another source when a neighboring body or star repeatedly flexes the planet. That mechanical stress produces internal friction and helps preserve warmth below an otherwise frozen exterior. In this case, the most important sea would never see starlight. It would remain sealed beneath an outer shell, protected from direct radiation, but also separated from the atmosphere. The thickness of the ice would depend on temperature, pressure, composition, and the strength of internal heating. Models allow liquid reservoirs under certain conditions, but their presence cannot be assumed from a frozen appearance alone. Even when a buried sea exists, its chemistry may vary sharply from the oceans on Earth. Salts, minerals, dissolved gases, in contact with the interior would shape whether the environment remained chemically active. At the other extreme, a planet can hold abundant water without possessing a clear sky or a calm liquid surface. Strong heating may turn much of the supply into a thick steam atmosphere. The pressure beneath that envelope could become immense. Clouds might block any view of the lower layers, while trapped heat kept the environment far above comfortable temperatures. A steam-covered planet could appear pale or bright from a distance, and still conceal a harsh surface below. Water vapor itself is a powerful greenhouse gas. As more liquid evaporates, the atmosphere can trap additional heat and encourage further evaporation. Under some conditions, this feedback may push the climate toward runaway heating. The presence of water then contributes to instability rather than moderation. A planet without continents would also circulate heat and material differently. On Earth, land interrupts currents, creates shallow seas, directs winds, and provides broad regions where rock meets water. A global sea would remove many of those boundaries. Currents could circle the planet through routes with no continental barriers. Storm systems might travel for enormous distances without crossing land. Nutrients released in one region could remain trapped in certain layers or become diluted across the planet. The absence of coastlines would remove environments where tides, sunlight, minerals, and changing conditions repeatedly meet. None of this makes life impossible. It simply means that an Earth-like biological path cannot be assumed. Habitability depends on more than the amount of liquid present. Pressure determines which physical states can exist. The atmosphere controls surface temperature and the movement of energy. The interior supplies heat and chemical material. Circulation decides where those ingredients travel. Contact with rock can influence whether useful compounds continue entering the sea. A planet may hold far more water than Earth while offering fewer opportunities for sustained chemical cycling. Another may look frozen and inactive while preserving a liquid environment below. A third may contain enormous quantities of water locked inside a dense atmosphere too hot for an open sea. The same substance can produce completely different planetary conditions. Blue does not necessarily mean gentle. Ice does not necessarily mean dry. Steam does not necessarily mean a living ocean waits below. Water widens the range of environments a planet can support. It does not by itself make that planet habitable. Gliese 436b moves around its star inside an enormous cloud of escaping hydrogen. From far away, the system can resemble a comet, with gas extending far beyond the region normally described as the atmosphere. The planet itself is not growing a solid tail. Its upper gases are being heated, expanded, and carried outward into space. Astronomers detect this extended material through ultraviolet light from the star. When the planet and its surrounding cloud pass across the stellar disk, hydrogen removes particular wavelengths from the light reaching Earth. The resulting shadow is much larger than the visible body alone could produce. That difference reveals an atmosphere spreading beyond the planet's usual gravitational boundary. The escape begins high above the deeper cloud layers. There, energetic radiation from the star strikes atoms and molecules in the upper atmosphere. The gas absorbs energy and becomes hotter. As it heats, it expands into regions where gravity has a weaker hold. Some particles continue colliding and exchanging energy until they move fast enough to escape permanently. Others are pushed outward by interactions with the star's particle flow. The process is gradual, but the combined effect can reshape a planet over immense spans of time. The upper atmosphere behaves like a thinning envelope, whose outermost material is continually carried away. Gliese 436b is massive enough to retain much of its deeper gaseous layer. Even so, the extended hydrogen cloud shows that the boundary between atmosphere and space is not always clean. Gas can remain associated with the planet while already moving beyond the compact region seen in ordinary models. It can surround the orbit, trail behind the body, and form a broad structure shaped by radiation and motion. On hotter planets, the escaping region may contain more than hydrogen. Observations of some close orbiting worlds reveal heavier atoms and electrically charged particles high above the layers where they would usually remain. Severe heating can lift material to great altitudes, while rapid outward flow carries it toward space. Elements normally associated with deeper, atmospheric regions may therefore appear far above the planet. This does not mean every atom leaves. Much of the gas may rise, cool, and fall back. The balance depends on temperature, gravity, composition, radiation, and the rate at which energy reaches the upper layers. A strong gravitational field makes escape more difficult. A hot atmosphere spreads outward more easily. A light gas, such as hydrogen, can depart faster than heavier material under the same conditions. Stellar activity can intensify the process through repeated flares and particle outflows. No single measurement describes the complete history. Researchers combine mass, radius, orbital distance, atmospheric signals, and models of the star's activity to estimate how much gas may have disappeared. The long-term result can be a change in planetary identity. A body that began with a thick gaseous covering may slowly become smaller as its outer layers erode. The remaining object can be denser, hotter, and more exposed than it was during its early formation. Some close rocky planets may be the cores of former sub-Neptunes, worlds once surrounded by larger envelopes of hydrogen and helium. Radiation could have removed much of that gas and left the inner structure behind. A small world may be what remains of a larger one. This interpretation is plausible for certain planets, but it does not apply automatically to every dense body near a star. Some rocky planets may have formed with little gas from the beginning. Others may have lost their envelopes during collisions, rather than through radiation alone. A similar present-day mass and radius can therefore emerge from different histories. Atmospheric erosion offers one path, not a universal explanation. The difference matters because two outwardly similar planets may contain very different interiors. One could be built mainly from rock and metal in its original form. Another could preserve the compressed center of a body that once resembled a small gas giant. The atmosphere can erase part of its own history, while the surviving core keeps the physical consequences. Loss also competes with replenishment. Volcanoes can release gases stored inside the mantle. Melting, impacts, and chemical reactions may add new material to the sky. A planet can therefore supply gas from below while radiation removes it from above. Whether the atmosphere grows, stabilizes, or continues thinning depends on which process dominates. A massive world with active geology may replace part of what escapes. A smaller body under intense radiation may struggle to maintain any substantial envelope. A cooler planet farther from its star may preserve light gases for much longer. Magnetic effects can alter how charged particles move around the planet, but they do not create a perfect barrier. The protection depends on field strength, atmospheric structure, stellar activity, and the direction of the incoming particle flow. Even Earth continually releases a small amount of atmospheric material into space. The difference on highly irradiated exoplanets is one of scale. There, the loss can become a central part of planetary evolution rather than a minor leak. The process may continue without any single dramatic moment. One orbit follows another. The star rises nowhere if the planet is locked, yet its radiation continues reaching the same upper layers. Hydrogen atoms drift outward beyond the main atmosphere. Their absence from the deeper envelope is too small to notice from one circuit alone. Across countless repeated orbits, however, the missing particles accumulate into a changed planet. The transformation is nearly invisible in real time. Only the extended cloud and the altered wavelengths of stellar light reveal that the sky is slowly leaving. This slow erosion changes how astronomers think about atmosphere. It is not simply a permanent shell placed around a planet during formation. It is a temporary balance between gravity, heat, chemistry, radiation, and material rising from the interior. A stable-looking sky may be continuously renewed. A thin one may be the remainder of something much larger. An exposed core may preserve the final state of a long contest between retention and escape. An atmosphere is not merely something above a world. It is something the world must continuously keep. WASP-12b is so close to its star that gravity has pulled the planet away from a relaxed, spherical shape. The side facing inward feels a stronger force than the side turned away. That difference stretches the body along the line between planet and star. The result is not a perfect ball, but an elongated world under constant stress. Tidal forces begin with a simple imbalance. Gravity weakens with distance, so the near side is pulled more strongly than the far side. Across an entire planet, that small difference becomes a global deformation. The atmosphere, the deeper gases, and even the interior respond to the unequal pull. Each orbit repeats the distortion, producing heat and spreading the outer layers beyond the region where they remain securely bound. WASP-12b appears to be losing material into the space around its orbit. Some of that gas may form an extended stream or diffuse cloud, rather than falling directly into the star. The planet is therefore not only being distorted, it is also being reduced. The process does not need to happen in one violent event. A small amount of gas can be removed during orbit after orbit, while the remaining body continues to look stable from far away. Over enough time, the loss changes both the planet and the environment around it. Tidal interaction can also alter the orbit itself. The planet raises a distortion in the star, just as the star raises one in the planet. Those bulges do not always remain perfectly aligned with the line connecting the two bodies. Their offset creates a torque that transfers rotational and orbital energy. Depending on the direction of that transfer, the planet may slowly move inward. The change during a single orbit can be almost impossible to notice. Only precise timing across many repeated circuits reveals that the path is shrinking. This is orbital decay. The planet continues following a familiar route, yet each circuit may carry it slightly closer to the star. From the surface, no sudden warning would appear in the sky. The star would look nearly the same from one orbit to the next. The atmosphere would continue moving, and the planet would keep turning or remain locked. Yet the long-term geometry would be narrowing beneath every apparently normal year. A world can complete countless stable-looking orbits while moving toward conditions it cannot survive. Some planets may lose their outer layers until only a dense center remains. Others may approach the point where the star's gravity overwhelms the planet's ability to hold itself together. At that boundary, material can be pulled away faster than the body can retain it. A planet can be unmade gradually. Disintegrating rocky worlds provide another version of the same idea. These small bodies pass close enough to their stars for intense heating to vaporize surface material. Dust and debris then stream away and spread along part of the orbit. When the material crosses in front of the star, the resulting transit can change from one passage to the next. One orbit may produce a deeper shadow, while the next produces a weaker or more irregular one. That variation suggests a changing cloud of debris rather than one clean solid silhouette. The planet may still possess a central body, but every circuit carries away another portion of its exterior. Destruction in this form is not a collision. It is a sequence. Heat loosens material, gravity shapes the escaping trail, and repeated loss gradually alters what remains. The process may continue until the object becomes too small to sustain the same level of shedding, or until little substantial material is left. Stars introduce a second route to planetary engulfment as they age. After exhausting fuel in their central regions, some expand into giants. Planets that once moved safely outside the visible surface may then find themselves inside the star's outer atmosphere. There, the planet encounters hot stellar gas rather than near empty space. Drag removes orbital energy, heating intensifies, and the path contracts more rapidly. A world that survived for ages can enter its final phase because its star changed around it. The planet does not need to collide with the former surface. The expanding atmosphere can reach the orbit first. Once immersed in that gas, the body plows through material, loses speed, and falls inward. Survival becomes increasingly difficult, even for a large giant planet. In some cases, observations can measure orbital change or detect gas leaving a close world. The final outcome, however, usually comes from physical models extending those measurements into the future. A shrinking orbit does not reveal the exact moment of disruption. An extended atmosphere does not prove how much material will survive. Researchers therefore separate the measured change from the modeled ending. The mechanics still point in one direction. A very close planet cannot remain unaffected by the difference in gravity across its body. It may be stretched, heated, eroded, and drawn into a tighter path. For most of its existence, the orbit may have seemed permanent. The same gravitational relationship that preserved repeated motion can also contain the mechanism that ends it. Gravity can hold a planet in place for ages and slowly remove the place it has to orbit. Kepler 51b is a planet that looks enormous when measured by width, yet contains surprisingly little mass for its size. Its outline suggests a giant, but its average density is extraordinarily low. This type of body is sometimes called a superpuff. The name describes a world whose outer envelope is greatly inflated around a much smaller and denser center. From far away, the measured radius can make the planet appear more substantial than the material inside it truly is. That mismatch immediately challenges the instinct to picture every large planet as a place with a clear exterior boundary. On Earth, descent ends at land, water, or another solid surface. On a gas-rich giant, there may be no single point where the atmosphere stops and ground begins. A visitor entering the upper clouds would continue downward through layers that gradually become hotter, denser, and more compressed. The sky above would fade behind thicker gas. Clouds would disappear. Pressure would build around the falling object from every direction. Still, no plain of rock would appear below. The visible cloud tops are only the outermost region of a much deeper structure. Beneath them, hydrogen, helium, water-bearing compounds, and other materials change their physical behavior as pressure increases. Gas becomes dense fluid without crossing one simple boundary that could honestly be called a surface. Deeper still, matter may enter compressed states that do not resemble ordinary air, liquid, or stone. The planet has an interior, but it does not offer a floor. Down remains meaningful. Floor does not. This is one reason descriptions of gas giants can be misleading. A photograph or illustration gives the body a crisp circular edge. In reality, that edge marks the altitude where the atmosphere becomes opaque enough to block the view. It is a visible boundary rather than a solid one. Cloud decks can strengthen the illusion. A bright upper layer may look calm, smooth, and almost tangible from space. Below it, temperature and pressure may rise through conditions no spacecraft or human body could survive. The apparent exterior is like frosted glass concealing a deeper room, except the hidden region continues for thousands of miles and never opens into familiar ground. Superpuffs make this uncertainty even more pronounced. Kepler 51b has a radius associated with a much larger giant, while carrying far less mass than such a giant would normally contain. One explanation is that a relatively modest center is surrounded by an extended envelope that contributes strongly to the measured width. The visible silhouette is oversized compared with the dense material at the center. Youth may help maintain that inflated structure because newly formed planets retain internal heat. Low gravity can also allow the outer gases to spread farther into space. Temperature, atmospheric composition, and ongoing escape all influence the measured radius. No single internal model explains every superpuff. Astronomers must test different combinations of core mass, gas composition, haze, temperature, and age against the same basic measurements. The planet may be wide because its outer gases are warm and expanded. It may also contain high-altitude particles that block light far above the deeper atmosphere. That makes the observed edge even less connected to a physical surface. Haze can hide composition in the same way frosted glass hides detail. When starlight passes through the outer gases, suspended particles may flatten or obscure the chemical signatures astronomers hope to measure. A seemingly featureless spectrum does not mean the atmosphere contains nothing. It may mean the deeper information is concealed beneath an opaque upper layer. Clouds can create the same problem. A bright deck may reflect light efficiently, while preventing observers from seeing hotter and denser regions below. The part that appears calm may be only the highest visible layer of a far more violent environment. Another planet, TRES 2b, demonstrates the opposite visual extreme. It reflects very little of the visible light falling onto it. From nearby, it might appear almost black against the surrounding space. The darkness does not mean the planet is cold. Its atmosphere absorbs much of the incoming light and still releases energy as heat. The result is a world that can be visually darker than charcoal while remaining intensely hot. Clouds or chemical compounds capable of reflecting light appear to be scarce in the observable upper layers. Absorbing gases and high temperature may combine to keep the planet dim in visible wavelengths. Yet even here, appearance remains incomplete. A dark exterior does not reveal the exact structure beneath it. It only shows how little visible light returns towards space. The contrast between Kepler 51b and TRES 2b shows how unreliable a planet's outline and brightness can be. One looks greatly inflated, the other looks almost lightless. Neither appearance provides a simple answer about the deeper interior. Mass and radius must be considered together. A large radius with little mass points toward low average density. A similar radius with much greater mass suggests stronger compression and a more tightly bound interior. Light reveals the uppermost layers, while gravity reveals how much material the planet contains. Only by combining both can astronomers begin to distinguish an airy envelope from a dense giant. A descent into either world would eventually leave ordinary weather behind. The pressure would erase familiar clouds and transform the surrounding material. The gas would become so compressed that the difference between atmosphere and interior lost its usual meaning. Above, the visible sky would already be gone. Below, no solid plane would arrive. The falling path would continue into hotter, denser, and less familiar matter until the object itself could no longer survive. There would be no dramatic moment when air became ground. The environment would simply change continuously with depth. These planets reveal why size alone cannot define structure. A broad silhouette may be supported by a thin, expanded envelope. A bright cloud top may conceal crushing pressure. An almost black atmosphere may still contain tremendous heat. The visible outline is not the planet's true edge in the earthly sense. It is only the depth at which light stops escaping cleanly. For worlds like these, the word surface becomes an approximation used for observation rather than a place where anything could stand. Down does not guarantee a floor, and a planet can possess a clear shape from space while offering no solid boundary anywhere beneath its clouds. Kepler 16b moves around two stars rather than one. The stars circle a shared center while the planet follows a wider path around both of them. Their positions constantly change, yet the system can remain stable for long spans of time. A circumbinary planet is a world that orbits both members of a binary star pair. Kepler 16c provided one of the clearest confirmed examples of this architecture. Its existence showed that planet formation can succeed even when the central sources of light and gravity are always moving. The disk from which the planet formed had to surround both stars while responding to their combined pull. Material within that disk experienced repeated disturbances, yet enough remained organized for a large body to assemble. The result looks unfamiliar without being unstable. If the planet possessed a visible surface, two suns could rise and set in changing combinations. Their apparent separation would widen and narrow as the stars moved around each other. Double shadows might overlap, separate, and change direction across the ground. Those details remain hypothetical because Kepler 16b is a gas giant, and no solid viewpoint has been observed. The important fact is the orbital structure itself. Stable motion does not require one fixed star at the center. It requires a pattern in which the bodies avoid destructive encounters. Other systems depart from the solar system in a different way. Most planets here move close to the same broad plane, reflecting their formation inside a flattened disk of gas and dust. Many distant systems follow a similar arrangement. Others appear to have been turned on their side. Some exoplanets travel on paths sharply tilted relative to the rotation of their stars. A few follow nearly polar orbits, passing above the stellar poles rather than circling close to the equator. This misalignment can arise through several different histories. A planet may form inside a disk, already warped by the pull of a companion star. In another system, several planets may begin in one plane before later encounters push one body onto a steeply inclined path. Long-term effects from a distant companion can also change orbital angles gradually. No single strange tilt reveals one certain cause. The geometry limits the possibilities, but it does not reconstruct every event. A companion star can disturb the planet-forming disk before the planets are fully assembled. Its gravity may bend the outer region while the inner material remains aligned differently. In extreme cases, separate parts of the disk can settle into distinct orientations. Planets forming there may inherit different orbital planes from the beginning. Elsewhere, the disruption comes later. Large planets can exchange energy through close encounters. One may move inward, another may be pushed outward, and a third may acquire a tilted path. The system visible today could be the surviving arrangement after other bodies were removed. Orbits can also differ strongly in shape. A nearly circular path keeps a planet at roughly the same distance from its star throughout the year. A highly eccentric path stretches into a long oval. The world then moves from a distant, cooler region toward a much closer and hotter passage before heading outward again. The amount of stellar heating can change dramatically during one circuit. Atmospheric layers may expand as the body approaches the star and contract as it retreats. Clouds can appear or disappear, while winds respond to the rapid change in temperature. One year may contain several sharply different climate states because the orbit itself creates the variation. Farther away, some giant planets occupy paths so wide that they challenge simple models of growth. The usual core building process works best where a young disk contains enough solid material for a large center to assemble before the gas disappears. At extreme distances, material is sparse and orbital motion is slow. Forming a giant, there may take longer than the disk remains available. One possibility is that part of the disk collapsed rapidly under its own gravity. Another is that the giant formed closer to the star and later moved outward through gravitational interaction. Some may have been scattered to remote paths without escaping the system completely. Each explanation can produce a similar present-day picture. That makes distance alone an incomplete record. Viewed from far above, the familiar flat diagram disappears. One planet circles two stars in a broad outer ring. Another crosses above the stellar poles on a steep path. A third follows an elongated orbit, spending most of its time far away before rushing through a close passage. Several orbital planes may intersect without the planets colliding. The arrangement can remain stable, even though it looks disordered from the perspective of our own system. Complexity and instability are not the same thing. A system can preserve unusual geometry for ages when its paths avoid destructive encounters and settle into repeatable patterns. The present architecture is therefore both an arrangement and a record. A tilted orbit may point toward an ancient encounter. A wide path can suggest outward scattering or a different formation route. A binary star can reshape the disk from which its planets emerged. None of these clues guarantees one complete history. Together, they show that planetary systems are not required to resemble the orderly flat structure familiar from our own neighborhood. An orbit is not merely a path through space. It is surviving evidence of forces that may no longer be visible. TRAPPIST-1 contains several roughly Earth-sized planets packed into a region that would seem almost empty by the standards of the solar system. All of them circle a small, cool star inside a space much narrower than Mercury's orbit around the Sun. At first glance, such compression seems unstable. Several full worlds move close enough for their gravity to influence one another during every circuit. Yet the system has not collapsed into immediate collisions. Its order comes partly from the timing of those repeated interactions. A cool star produces less energy than the Sun, so planets can orbit nearby without automatically receiving unbearable levels of heat. Their distances remain small, but distance alone does not determine temperature. The brightness of the star matters just as much. From a hypothetical surface, neighboring planets could appear unusually large in the sky. One might drift overhead as a visible disk rather than as a point of light. Its changing position could reveal the compact architecture of the system without a telescope. No actual surface view has been recorded, and clouds or haze could hide the surrounding worlds completely. The scale of the orbits, however, is firmly measured. Several planets in TRAPPIST-1 participate in a chain of orbital resonances. Resonance means that their orbital periods maintain repeating numerical relationships. One body may complete several circuits during the time a farther neighbor completes fewer. The exact positions do not repeat perfectly during every passage, but the broader pattern returns again and again. That repeated schedule organizes how the planets pull on one another. A gravitational tug delivered at a similar point in each cycle can reinforce a stable relationship rather than create random disruption. Resonance does not remove interaction, it gives the interaction structure. The system resembles clockwork only in the limited sense that each moving part affects the timing of the others. There is no rigid mechanism holding the planets in place. Gravity alone preserves the repeating arrangement. Each planet moves according to the combined influence of the star and its neighbors. If one body arrives slightly early at a particular position, its pull can alter the timing of another. Later interactions may correct part of that shift. Over many circuits, the system maintains a linked pattern rather than a collection of isolated paths. Astronomers can measure these relationships through transit timing variations. A transit should occur on a predictable schedule when a planet repeatedly crosses its star from Earth's point of view. In a system with only one planet, those passages would follow a highly regular interval. When neighboring worlds add their own gravitational influence, the crossing can happen slightly early or slightly late. The difference may be small, but repeated measurements reveal a clear pattern. Those timing changes provide information about mass. A heavier planet produces a stronger effect on its neighbors than a lighter one in a similar position. By comparing the early and late arrivals of several transits, researchers can estimate how much material each body contains. The method can reveal interactions that would remain hidden in a simple measurement of size. It can also point toward an additional companion whose pull disturbs the observed schedule, even if that body does not cross the star itself. A planet can therefore announce a neighbor through lateness. The system's precision is not necessarily evidence of a peaceful beginning. Compact planetary arrangements may form farther out and then move inward through the surrounding disk. As several planets migrate together, gravitational interactions can trap them into resonant chains. The gas and dust eventually disperse, leaving the linked arrangement behind. Not every original body needs to survive that process. Early systems may contain more planets than remain at maturity. Some can collide and merge into larger objects. Others may be pushed onto unstable paths or removed from the inner region. The worlds visible today could be the survivors of an earlier period of crowding and loss. Their current order may have emerged only after less stable arrangements disappeared. This possibility helps explain why resonance is both a sign of stability and a clue to migration. The repeating relationships preserve information about how the planets moved while the system was young. They are not a complete history, because later interactions can alter or break resonances. Even so, the surviving chain places limits on what could have happened. Moons would add another layer to these compact systems. Natural satellites are likely to exist around some exoplanets, but confirming them remains extremely difficult. A moon is smaller than its planet and usually produces a much weaker signal. It may slightly change the depth or timing of a transit. The planet's own interactions with neighboring worlds can produce similar effects. Instrument noise and stellar activity can create additional confusion. For that reason, candidate exomoon signals require exceptional caution. An unusual transit does not become a confirmed moon simply because one model can explain it. The signal must repeat, resist alternative interpretations, and remain consistent across independent observations. No uncertain candidate should carry the same weight as the confirmed planets in TRAPPIST-1. The known system is already complex enough without adding unverified companions. Several worlds circle at different rates while continually changing one another's schedules. One passes the star, then another follows. A neighboring body pulls slightly ahead, while a later interaction changes the interval again. After many circuits, similar configurations return. The planets do not move independently through empty lanes. Each orbit is part of a connected gravitational arrangement. Multiple years unfold around the same small star, each measured by a different interval. The shortest calendars repeat rapidly, while the outer worlds complete their slower circuits. Every passage alters the conditions for the next. The system remains crowded, but crowding alone does not make it unstable. Stability can emerge from precisely repeated interaction. Rogue planets move through interstellar space without orbiting any star. They have no sunrise ahead of them and no familiar source of daylight behind them. From the outside, such a world would appear almost completely black against the surrounding darkness. It would still possess mass, motion, gravity, and an internal history. Such bodies may arise through more than one path. Some could form in isolation when a cloud of gas collapses into an object too small to become a true star. Others may begin inside ordinary planetary systems before gravitational encounters throw them outward. In a crowded young system, several large bodies can repeatedly pull on one another. Each encounter exchanges energy and changes the shapes of their orbits. If a body gains enough speed, the system can no longer hold it. Ejection does not require an explosion or a direct collision. It can result from a sequence of close encounters, each one altering the orbit until escape becomes possible. A passing star may also disturb a weakly bound outer world and remove it from the system. After ejection, the bright geometry of days and seasons disappears. There is no stellar year defined by circling a parent sun. No heated side turns toward a central source, and no ordinary dawn moves across the exterior. The surface, if one exists, cools towards the temperature of the space around it. That sounds like the end of every active process. It may not be. The body carries energy within itself before it ever receives light from a star. During formation, falling material releases heat as gravity compresses the growing body. Impacts add more energy, while dense materials sink and lighter layers rise. Some of that original heat can remain stored in the interior for a very long time. Radioactive elements provide another source. As unstable atoms change into more stable forms, they release small amounts of energy. Across an entire mantle, that slow release can help keep deep layers warm. A large free-floating world may therefore cool far more gradually than its dark exterior suggests. The outer region could approach the cold of interstellar space while the interior remained active. Volcanism or slow movement within the mantle might continue beneath the frozen exterior. A thick, hydrogen-rich atmosphere could strengthen that separation. Hydrogen can slow the escape of internal heat when it forms a deep enough envelope. Under suitable conditions, the pressure and insulation might allow liquid water to persist near the surface or farther below. This is a theoretical possibility, not an observed ocean. The idea comes from models combining mass, atmospheric thickness, internal heat, and the behavior of water under pressure. A different structure could preserve liquid beneath an icy shell. The exterior might freeze into a thick crust, while deeper layers stayed warm enough to remain fluid. Ice above would reduce heat loss, acting as a roof over a buried reservoir. Below it, radioactive decay and leftover formations' energy could continue warming the rock. If water separated the ice from the interior, the deepest sea might interact with minerals and volcanic material. That contact could supply chemical energy even without sunlight. A small body may lose heat too quickly. A larger one may retain more warmth, but also produce pressures that force water into dense forms. An extremely thick envelope could create a high-pressure environment unlike any open ocean on Earth. The planet must retain enough heat, preserve the right materials, and slow cooling without eliminating the liquid state. None of this establishes habitability or life. It only shows that starlight is not the sole source of planetary energy. The most striking contrast lies between the exterior and the layers below. Outside, no clouds would catch sunlight because there would be no sunlight to catch. No illuminated horizon would separate ground from sky. The upper atmosphere might be visible only through faint heat escaping at infrared wavelengths. Beneath that unlit envelope, pressure would rise. Deeper still, the interior could remain warm, moving, and geologically active. An ember of formation heat might survive inside insulation while the surface crossed the galaxy in darkness. This does not make the world Earth-like. It makes it self-contained. These objects also complicate the meaning of a planetary system. A world can begin as part of one arrangement and later become independent of it. A gas-rich body might carry moons into interstellar space. A rocky one could retain scars from collisions that happened before ejection. Without a parent star, astronomers lose many of the easiest detection methods. Some free-floating worlds can be detected through gravitational microlensing, when their gravity briefly magnifies a background star. Young massive examples may also glow faintly through retained infrared heat. Many such bodies may pass unnoticed because they produce no convenient repeated signal. Each one would still be shaped by formation, chemistry, gravity, and chance. It would simply no longer belong to a sun. A planet can lose its star without losing every source of energy. The first confirmed exoplanets were not found around a calm star like the sun. They were discovered around a pulsar, one of the most compact and violent objects left behind after a massive star transforms. That reversal changed the early search for distant planets. Worlds were expected around ordinary stars with broad disks of gas and dust. Instead, the first clear evidence appeared beside an object created through stellar destruction. A pulsar is a neutron star rotating at extraordinary speed. It contains more mass than the Sun compressed into a sphere only a small distance across. Beams of radiation emerge from regions near its magnetic poles. As the object turns, those beams sweep through space. When one crosses Earth, telescopes receive a pulse. The effect resembles a distant lighthouse only in the repeating appearance of the beam. The physical source is far more severe. Matter inside a neutron star is compressed beyond anything found in ordinary planets, while the surrounding space is filled with powerful radiation and magnetic fields. What makes a pulsar useful for planet detection is the regularity of its pulses. Each arrival can be timed with exceptional precision. An orbiting body pulls slightly on the neutron star and shifts its position around their shared center of gravity. That movement causes the pulses to arrive a little earlier or later than expected. A repeating timing pattern can reveal the presence of planets even when no transit or direct image exists. The method is sensitive enough to expose small companions through changes that would otherwise remain hidden. The discovery created an immediate question. How could planets exist around the remains of a star that had passed through such a destructive transformation? One possibility is survival. A planet originally orbiting far enough away may endure the event that creates the neutron star. That survival would demand a favorable combination of distance, direction, and orbital change. The star loses mass during its transformation, altering the gravitational structure of the system. A violent explosion can also deliver an uneven push to the remaining compact object. Nearby planets may be thrown out, pulled into new paths, or stripped of much of their atmospheres. One that remains bound could end up circling a central object very different from the star around which it formed. Survival is not the only explanation. Some planets may assemble after the original stellar transformation. Material expelled or left behind can settle into a new disk around the compact object. Dust, gas, and heavier elements within that disk may collide and gradually form second-generation planets. These worlds would not be survivors of the first planetary system. They would be new bodies built from its remains. A third possibility involves later capture or rearrangement. Gravitational interactions with a companion star may bring material or planets into new orbits after the pulsar has already formed. Different systems may preserve different histories, and no single explanation accounts for all of them. One especially unusual pulsar companion has often been described as a diamond planet. The popular name creates an image of a glittering solid world. The physical interpretation is more complicated. The object may be the stripped core of a former star that once transferred much of its outer material to the pulsar. What remains appears unusually rich in carbon and extremely dense. Under high pressure, some carbon may take crystalline forms. That does not mean the object possesses an accessible surface made from clear gemstones. It may not be a conventional planet at all. It could instead be the compact center of a stellar companion reduced to planetary mass. The label simplifies an uncertain history into one memorable phrase. The deeper interest lies in what the companion represents. The boundary between planet and stellar remnant can become difficult to define when one body has lost nearly everything except its compressed center. A world-like object can form through destruction rather than through ordinary planetary growth. Elsewhere, the system nicknamed Methuselah carries another kind of challenge. It contains an ancient planet associated with a pulsar and a white dwarf. A white dwarf is the dense core left after a star like the Sun releases its outer layers. The planet belongs to a system formed long before the solar system existed. Its age shows that planetary construction began surprisingly early in galactic history. The young universe contained fewer heavy elements than it does today. Those elements are essential for building rocky cores, dust grains, and many of the solid materials found in planets. Astronomers once expected early systems to struggle because the necessary ingredients were less abundant. The existence of such an ancient planet shows that world building could begin even when the galaxy was chemically less developed. It does not prove that early planets were common. It demonstrates that they were possible. Around these transformed stars, daylight no longer resembles the steady warmth of an ordinary sun. A planet may circle a compact object whose original stellar form has disappeared. The system could contain radiation, debris, and altered orbits left by events that happened before the planet reached its current path. If the body survived, it carries evidence of an environment that changed almost beyond recognition. If it formed later, its material came from the remains of that change. In either case, the present system cannot be understood by looking only at what exists now. The missing star is part of the planet's history. The missing atmosphere may be part of it as well. So are the altered orbit, compressed companion, and debris that no longer remain visible. Planetary formation is usually described as a beginning. Around stellar survivors, formation can also follow an ending. Some worlds may endure their star's transformation. Others may emerge from material released during it. A few may be the reduced centers of objects that were once stars themselves. The categories overlap because nature does not preserve the boundaries used for convenience. A planet can continue orbiting after the central star has ceased to exist in its familiar form. Its history can cross stellar transformation and still resist one simple explanation. A young giant planet can sometimes be seen because it still glows with heat left over from its own formation. It does not shine like a star through nuclear fusion. Instead, it releases energy stored while the body was being assembled. Gas fell inward under gravity, material collided at high speed, and the growing interior became compressed beneath its own weight. Each process produced heat. Some of that energy remains trapped long after the surrounding disk begins to fade. At infrared wavelengths, a newly assembled giant may therefore appear as a warm point beside its star. The glow provides direct evidence that the planet is still cooling. This makes young, massive worlds easier to photograph than smaller, mature planets, even when the mature bodies are closer to Earth. An older giant may have released much of its original heat and blend into the darkness beside its star. A younger one can remain warm enough to separate from the glare. The image may reveal little more than position, brightness, and color. Even so, that faint light contains information about temperature, mass, atmosphere, and the way the planet formed. Early heat comes from several sources. As gas and dust fall toward the growing body, gravity converts motion into thermal energy. Impacts deposit more heat into the outer layers. Dense materials sink toward the center while lighter material rises, releasing further energy as the interior separates into layers. The young planet becomes a reservoir of its own construction. How quickly it cools depends on mass, composition, cloud cover, and the efficiency with which heat escapes through the atmosphere. Two planets of similar size can therefore glow differently if their formation histories were not the same. A body assembled rapidly may begin hotter than one built more gradually. A violent impact can add energy long after most growth has ended. A thick atmosphere may slow cooling and preserve brightness for longer. Direct images capture only the surviving heat, not every event that produced it. The surrounding disk offers another view of planetary formation in progress. Young stars are often encircled by gas and dust, arranged into broad, flattened structures. Within them, grains collide, stick together, and gradually build larger bodies. At the same time, gravity, radiation, magnetic effects, and pressure shape the material into rings, gaps, spirals, and clumps. Some of those features are consistent with planets already forming inside the disk. A growing body can clear material from its path or pull nearby gas into a spiral. It may create pressure changes that trap dust along a ring. A massive hidden planet can also disturb the movement of gas without being directly visible. These patterns are valuable clues, but they are not automatic proof. Disk physics can produce gaps and rings without a planet. Magnetic interactions may shift gas. Dust can collect where pressure creates a stable trap. A sharp structure becomes more convincing when several independent measurements point toward the same concealed body. From far away, the disk may appear calm and symmetrical. Up close, it would be crowded with collisions, drifting grains, changing pressure, and material moving toward or away from the star. Dark gaps would cut through brighter rings, while spirals stretched across the dusty surface. The forming planets might remain buried inside the same material they were reshaping. Their presence would be visible first through absence, motion, and distortion. The early system may contain more bodies than the mature system eventually keeps. Young planets do not grow in isolation. They exchange energy with the disk and with one another. As their masses increase, their gravitational influence reaches farther across neighboring paths. Close encounters can alter orbits quickly. One body may be pushed toward the star. Another may move outward. A third may leave the system completely. Collisions add another possible outcome. Two growing planets can merge into one larger body. The impact may melt much of the exterior, mix previously separate layers, and change the final rotation. In other cases, the collision can remove part of an atmosphere or throw debris into orbit. A large impact does not simply destroy. It can build, strip, reshape, and chemically transform. The mature planet left behind may contain the combined interiors of several earlier bodies. Its moons may form from the debris. Its atmosphere may be thinner because of the violence that created its final mass. The calm surface observed later can hide a history of repeated assembly. Gravitational scattering produces changes without direct contact. Several large planets can pull on one another until their original paths become unstable. Some move inward into regions of stronger heating. Others are thrown onto wide, tilted, or stretched orbits. One may escape and become a free-floating world. The survivors settle into the arrangement astronomers measure much later. A quiet system is not proof of a quiet beginning. It may be the final structure left after collisions, ejections, and migration remove the unstable alternatives. This changes how a present-day planet should be interpreted. A rocky body may be an original product of its birth region. It may instead be the exposed core of a former gas-rich planet. A large world could be the result of several mergers. A distant giant may have formed closer to its star before being scattered outward. The orbit, composition, atmosphere, and rotation all carry pieces of that earlier history. What is missing can be evidence as well. An empty gap between surviving planets may mark the loss of another body. A thin atmosphere may preserve the consequence of an ancient collision. An unusual tilt may record an encounter whose other participant no longer remains nearby. Astronomers reconstruct these biographies from incomplete traces. They compare heat, age, density, orbital geometry, disk structure, and atmospheric composition. No measurement tells the whole story alone. Together, the evidence can narrow the possible histories without reducing every system to one certain sequence. Some planets observed today are younger than ancient branches of life on Earth. They are still releasing formation heat, while our own biosphere continues after billions of years of change. Around their stars, dusty disks may still be settling. New collisions may still occur. Orbits may not yet have reached their final arrangement. The word planet can sound like the name of a finished object. In young systems, it often describes something unfinished. A planet is a biography written in heat, orbit, composition, and everything that no longer remains around it. The habitable zone sounds reassuring because it places a planet at a distance where surface water might remain liquid. That definition is useful, but it answers only one narrow question. It does not reveal whether the body has an atmosphere, whether that atmosphere traps too much heat, or whether surface pressure allows liquid water to exist. A body can occupy the right orbit and still be hostile to every form of life known on Earth. A thick envelope rich in heat-trapping gases may drive temperatures far above the boiling point of water. A thin one may fail to move warmth between regions, leaving one side hot while the other becomes cold enough for gases to condense. Clouds complicate the picture further. High reflective layers can return incoming energy to space, while others trap infrared heat below them. The same world can therefore cool or warm depending on where clouds form, what they contain, and how long they persist. Oceans and continents also shape climate through circulation, erosion, and the movement of nutrients. A global sea may transport heat efficiently, but lack many coastal and geological boundaries that support chemical exchange on Earth. The star introduces another layer of uncertainty. A temperate orbit around a red dwarf may place the planet close enough for tidal locking. One side could remain under constant light, while the other receives none. A dense atmosphere might redistribute enough energy to prevent atmospheric collapse. A weaker one could leave the dark side cold enough for important gases to freeze. Strong stellar flares can break apart molecules, heat the upper atmosphere, and accelerate the escape of gas into space. None of these outcomes follows from orbital distance alone. The habitable zone is closer to an address than a description of the house. It identifies where the body is, not what conditions exist there. Contact between water and rock may matter just as much as temperature. Chemical reactions beneath the sea can move carbon, minerals, and other elements through cycles that help regulate climate. If high-pressure ice separates an ocean from the rocky interior, much of that exchange may be restricted. A water-rich world can contain abundant liquid, while lacking the pathways that keep Earth's environment chemically active. Magnetic effects are often presented as a simple shield against stellar radiation. The reality is more complicated. A magnetic field can redirect some charged particles, but it cannot block every form of radiation. Its value depends on atmospheric depth, stellar activity, and the geometry of the interaction. A body without a strong global field does not automatically lose its atmosphere, and one with a field does not automatically preserve it. Gravity creates another major difference. A massive rocky body may retain a deeper atmosphere, while a smaller one can struggle to keep light gases over long periods. Stronger gravity would also change how bodies move, how clouds settle, and how quickly material falls. Mass influences pressure, atmospheric survival, internal heat, and geological activity at the same time. These factors do not operate independently. A thick atmosphere changes temperature, temperature changes circulation, and circulation changes clouds. Clouds alter the energy balance, which determines whether surface liquid remains stable. Habitability is not a ring drawn around a star. It is a temporary agreement among many physical processes. Possible liquid water also exists beyond the traditional zone. A frozen world or moon may preserve a buried ocean through radioactive heat or tidal flexing. Ice can insulate the layers below and slow the loss of energy into space. Such an environment would receive no direct sunlight, yet it might remain chemically active where liquid meets rock. This possibility does not establish life. It shows only that surface warmth is not the sole route to a liquid environment. The same caution applies in the opposite direction. A body inside the traditional zone may enter runaway heating, lose much of its atmosphere, or develop pressure conditions that prevent an Earth-like surface. Optimism and pessimism both become unreliable when they depend on distance alone. Even this broader picture is limited by what telescopes can detect. Transit surveys favor bodies whose orbits cross their stars from our point of view. Radial velocity works best when a planet creates a strong measurable motion in the star. Direct imaging favors young warm giants separated far enough from stellar glare. Gravitational microlensing can reveal distant systems, but many events are brief and do not repeat. The catalog is shaped by visibility. Large worlds close to their stars are easier to find than small cold bodies on wide orbits. An Earth-sized planet may remain hidden simply because its orbital plane never produces a transit. A distant rocky body may create too little stellar motion for present instruments to separate from noise. An old giant may have cooled until its glow is too faint to isolate. A small frozen body on a wide path could complete orbit after orbit without producing a convenient shadow, strong wobble, or visible point of heat. It would still possess weather, chemistry, gravity, and history. It would simply fall outside the easiest methods of discovery. Thousands of confirmed worlds therefore represent a filtered sample rather than a complete inventory. The known systems show what nature can produce, but they do not define its outer limit. The galaxy's most common world may belong to a category that current surveys rarely detect. Some combinations of mass, atmosphere, orbit, and interior may not yet have names. The familiar words now return with narrower meanings. Rain describes whatever material can condense and fall under local conditions. Ocean describes a liquid layer that may never touch rock or sunlight. Day describes rotation and illumination, not necessarily sunrise and sunset. Year describes an orbit that might last hours or centuries. Sky describes an atmosphere that may be thick, escaping, mineral-rich, or almost absent. Ground describes a boundary that some worlds never provide. Each word belongs to local physics rather than one universal model. Far beyond the reach of present instruments, a small cold planet may now be moving through a wide and silent orbit. It casts no shadow across its star from Earth. Its pull is too weak to measure. Its remaining heat produces no visible point beside the stellar glare. Yet it is real, carrying conditions that may fit no category astronomers have created so far.